Welcome to 33rd lecture for the NPTEL course on computer system optimization for machine learning. Today we will continue on Saarthi serve, and then we will discuss about distributed service, which is again another paper called DistServe. We will see that. So, in the last lecture we discussed the main idea behind Saarthi. The first one shows vLLM, which prioritizes the prefill. That is why while like another the prefill request of B comes, then it stalls the decode. So, the total latency after the total latency at which the next token of the request A is generated is 24 millisecond, which does not satisfy the service level objective. We can push the entire prefill and decode together to the compute, and that also actually does not meet the service level objective. Here it is 16 millisecond, which is again greater than 10 millisecond, right. Now, in Saarthi, instead of pushing the entire prefill with decode, the authors chunk the prefill, and the chunks are the chunks are selected in such a way that they are just enough to consume the leftover compute budget in decode batches. Now, here you can see that once it is chunked, the prefill of B is chunked in BP1 and BP2. The latency of the next decoded token is just 9 millisecond. The next latency of next decoded token from A is just 9 millisecond, which is a gain, right. Gain in the sense we still did not violate the service level objective, and at the same time we actually launched the prefill of B, right. We did not stall the prefill of B entirely. Now, let us take one example, like the real example with many tokens getting generated. So, this is again in the baseline iteration level scheduling, we will have this prefill of A, prefill of B, C, D, and then let us say another. So, this is the time axis, the x axis is time, and then let us say we have this A, B, C, D, probably you can think as the different request. Then let us say another prefill A, B, C, D comes. So, here you can see that after this D is over, since prefill is going on, prefill of this B is going on, that is why we have to stall, like that is why there is a bubble here, okay. And after this prefill of B is done, we can start the decode of A and B. So, it will, and then it will go on like that, okay. Now, let us say the prefill of A, B, C, D can be chunked, and let us assume that prefill of A can be chunked into AP1, AP2, prefill of B can be chunked 3-way, prefill of C can be chunked 2-way, and prefill of D also can be chunked 2-way. This is the chunked composition, correct. Now, with Saarthi, we can schedule these chunked prefills with decode maximal batching. So, what we can do is we can chunk this AP1, AP2. So, we can think that A is a type of request, okay, and then probably there are multiple requests going on in the GPU. Okay. So, AP1, BP1 can be scheduled, then AP2 and then BP2 will come. Now, as you can see that now the prefill of A is done, right. Now, if prefill of A is done, that means the decode of A can start, correct, and we will start the decode of A. At the same time, we can also start the prefill of C, okay. So, as you can see here, we started prefill of C as well as the decode of 1. So, now we did not stall. So, here we stalled this decode of A because some decode of B was going on, right. So, we made sure that the latency, if you look carefully, the width of all these chunk prefill is exactly the same, okay. So, we made sure that the chunk prefill and the decode will be enough to occupy the entire GPU, okay. So, that is why you can see that this chunk prefill of C and then A, the decode of A is computed together. Then remember B, the prefill of B is not over. So, the prefill of B is scheduled, and then prefill of D is scheduled with that prefill of D. another decode is scheduled, and so on and so forth. So again with prefill of C, another decode of B. So now since 3 prefill of B or 3 chunks of B is done, so we can start the decode of B, right. So with prefill of, with the second chunk of prefill of C, we started the first decoded token or first decode of B. So this will go on. I mean, still there will be some bubble, but we are actually, see here we finish D decoded token, first decoded token of D here, right, at this point of time, but here we finish the first decoded token of D at this point of time, correct. So there is a good amount of latency saving. So this much latency is saved between prefill prioritized policy and Sarthi, correct. Now one obvious question is how to pick the chunk size, right. I mean, how can we pick the chunk size so that it is not too big to like oversubscribe the GPU, and it is not too small to underutilize the GPU a lot, okay. So when we pick the chunk size, we need to make sure that we have to pick the chunk size which meets the time between token. I mean, we should not pick a very large chunk size so that the decode latency is getting harmed, right, because the time between token has to be maintained, the time between token has to be low, correct. That is why larger chunk is not always better, because it will oversubscribe the GPU, and then it will increase the time between token, right. Now we can do tile quantization in GPU matrix multiplication, which is nothing but extraneous computation if tensor shapes are not a multiple of the tile size. Now let us see. So this is one example, per token cost, right. So the x-axis is sequence length and the y-axis is iteration time, right. So again the sequence length is during prefill, sequence length of prefill, right. So you can see there is a step like behavior. I think if you remember during pruning we also showed this kind of step like behavior, right. So from this kind of behavior we can I mean again we can profile and see what is the decode latency, and from this kind of step like behavior we can like take we can what should I say, I mean we can choose the chunk size, right. Again each chunk should be multiple of the tile size. Tile size is nothing but GPU tiles, okay. So let us say each tile can hold let us say 8 tokens. That means our chunk size should be multiple of 8, okay. So here in this case probably the tile size is 128. So you can see that when we increase the sequence length from 128 to 256, then there is a or when the sequence length is increasing from 255 to 256, then there is a increase in the tile size, increase in the iteration time, because it is going to the next tile, the computation is going to the next GPU tile. So it is taking more latency or more time, right. So here you can see that from this table you can see that if the chunk size is 128, then per token time is 0.43, 256 0.27, and then at 257 the per token time is 0.36, right. So there is a huge jump between 256 to 257, right. So that is the thing we have to take care. So that means so this 0.27 and 0.36 is coming from this particular part of the curve. So we have to carefully choose the chunk size, right. I mean we should not choose the chunk size here, because there is not much difference in latency between here and here. So it is probably better that if we choose the highest chunk size given we have similar latency profile, okay. So that is how we can pick the chunk size. Now let us see the result of Sarthi. Now we already have seen few of the technique like Orca prioritizes decode, vLLM prioritizes prefill, and Sarthi tries to make a good balance, strike a good balance between prefill and decode, okay. So the setup here is shared GPT-4 trace on A100 GPU with strict and relaxed latency SLO. So, there is SLOS and SLOR. Strict SLOS is strict SLO means the service level objective has to be maintained, and relaxed is probably, I mean, we can maintain x some x number of x percentage of service level objective. The experiments are shown for Llama 270 billion and Falcon 180 billion. Okay. The y axis is maximum capacity. So, when we say maximum capacity, that is nothing but like how many requests can be served. So, as you can see that when we go from decode prioritization to prefill prioritization, we can have the maximum capacity increases not much, but then Sarthi increases the maximum capacity by a huge margin, both with respect to Orca and vLLM. Okay. So, that is the gain. I mean, when we say max capacity, that means how many of the tokens or how many of the requests are actually satisfying the service level objective. That is the maximum capacity. So, as you can see that higher number of requests satisfy the service level objective with Sarthi serve. Okay, that is the gain of Sarthi serve, and then it has like 5 to 6 times higher capacity than Orca or vLLM. Okay. Now, let us see one example or let us see one demo where we are comparing between, or where it is compared between vLLM and Sarthi serve. Okay. So, there are two prompts. One is, I mean, not two prompts, we have exactly the same prompt. One is being executed with vLLM, another is executed with Sarthi. Okay. Now, we will show you two figures. The left hand side figure will show the number of token processed versus execution time, and the right hand side figure is showing the tokens per second for vLLM and Sarthi. So, we will see during inference how this tokens per second as well as number of tokens processed by versus the execution time changes between vLLM and Sarthi. So, remember vLLM prioritizes prefill. Okay. So, during prefill there will be no tokens per there will be no tokens generated, right. And Sarthi, I mean, since Sarthi does not stall prefill or even decode, it will always generate the token. Now, let us see how this sees. So, now as you can see, the blue is vLLM. So, now if you see, vLLM will have this flat region. During this flat region, we are only having prefill. Okay. No decode is happening. Now, Sarthi processes less number of tokens because Sarthi is scheduling both prefill and decode. So, it generates less number of tokens, but then it does not have any flat region like this. You can see there are flat regions here, etc. Correct. During those flat region, vLLM only performs the decode, and that actually is harmful for the entire decoding, because during that particular time no decoded token is generated, but Sarthi still is generating some tokens, right. So, that was in terms of token processed versus execution time. Now, let us see the tokens per second. I will run this demo again. Yes. So, tokens per second with vLLM will be higher initially when it is only decoding, right. Now, you will see sudden drop in tokens per second. Now, this drop happens when vLLM is prioritizing the prefill. During prefill, no decode is happening, right. But Sarthi actually maintains a good tokens per second during the entire decoding or during the whole for the entire batch, right. So, it never drops. During Sarthi or with Sarthi, the tokens per second never drops. In vLLM, with vLLM, the highest token per second or the peak token per second might be very high, because it is scheduling only the decode. During decode, there is no prefill. It might be very high, but then this sudden drop actually harms the entire batch. Okay, I hope you understand what is the difference between vLLM and Sarthi, right. So, at the end of the day, you can see that the batch finishes here, the entire batch finishes here, maybe at, let us say, 38 millisecond or 38 second mark, but with vLLM it finishes here, where we have this 50-second mark, or maybe it is finishing here 40 versus 50. So, it is like 25% improvement in latency, right, or maybe not 25, 20% improvement in latency, which is huge, correct. So, now the bottom line is, so remember, why did we even have this course? I mean, this course is not about machine learning, right, this course is about computer system optimization for machine learning. We have exact same algorithm, we have exact same machine learning algorithm, in this case probably some GPT algorithm, but then we are running in completely two different way. In one, I mean, when we run in one technique, there is some optimization, in both of the technique there is some optimization, of course, but in one technique the optimization is better in than the other technique. When we say optimization, these optimizations are these optimization primarily target the computer system. We have exactly the same algorithm, exactly same GPT-2 is getting executed by Saarthi and vLLM, but the only difference is there is some optimization specific to the computer system, so that the latency of one technique is providing good service level objectives than the other, and 20% improvement in latency is lot, right. So, you may think that okay, this GPT, Chat GPT, Claude, Gemini, these algorithms do wonder. Yes, the algorithms are very good, but then if we do not have innovations in the computer systems front, then those algorithms are useless, right. So, nowadays if you want to know something from Chat GPT, you just type out your prompt and then the Chat GPT gives you the result immediately, right. Now, that immediateness, the very less latency, that feature where this very less latency comes from the optimization in the computer system. Okay. So, I mean, again, the bottom line is, yes, we need to make newer ML algorithm to do task which can do wonder, but at the same time we need to have innovations in the computer systems front, so that those algorithms can run in good, like in reasonable amount of time, they can run in with reasonable amount of energy, etc. And this particular technique, the Saarthi versus vLLM, is probably one of the very good example that the same algorithm, you have the same algorithm, but if you run in two different ways, there is a huge difference in execution time, right. Now, with that, let us summarize Saarthi. The problem which we were targeting is state of the art system sacrifice decode latency to achieve higher throughput. The key insight behind Saarthi was that the arithmetic intensity of decode is low, right. So, that allows adding compute intensive prefills with negligible decode latency cost. Okay. And the key result which we saw is we achieve, I mean, it is not we, Saarthi achieves optimality in both latency and throughput simultaneously, leading up to 6 times higher capacity under SLO constraints. Okay. And Saarthi is like available in all major serving frameworks and more. I did not, I forgot to put the reference of Saarthi. It's a like published paper. You can go and search in Google, and it was published by the folks in Microsoft Research India. Okay. So, you can and the code is also available online. Okay. So, you can go ahead and take the code and then play with yourself to see how it makes difference, how Saarthi makes difference during batch processing. Okay. Is this a perfect solution? The answer is no, otherwise we would have ended the course here. So, yes, balancing low latency and high prefill throughput is very difficult task. Okay. Now, when we say chunking, yes, chunking is very nice. We can do chunking, we can push behind decode, we can piggyback the chunks behind decodes and all those things. But then overhead of this chunking increases as chunk size reduces, right. We need smaller chunks for lower time between tokens, right. So, if you think, let us say you have a long rope, right. Now, if I ask you to cut the rope in 2 halves, that is easy. But if I ask you to cut the rope in 100 pieces, that is difficult. That is difficult in the sense that will take more time, right. The that's, I mean, there will be a overhead of chunking, right, overhead of cutting the rope in 100 pieces. So that overhead of chunking increases as chunk size reduces, and again remember we need smaller chunks, right, for lower TBT. So let us say your prefill has like maybe 100 tokens and our chunk is only 10, that means we have to chunk the prefill 10 way, right, we have to make 10 pieces out of the chunk, correct. Now if we do lower smaller chunks, then the problem is the prefill throughput is low, right. If we cut the chunk in like smaller sizes, that means you have to have many chunks, and then you have to have that many rounds to finish the chunk. So again this particular figure is showing or characterizing the overhead of chunk. Let us say the prefill length, the x axis is the prefill length, and they are showing the overhead of chunk between the chunk size of 512, 1024 and 2048. So as you can see, when we have the chunk size of 512, the overhead is higher compared to 1024 and 2048. So the overhead reduces as we increase the chunk size, right. So that's why we need to know what's the good chunk size. Now again another problem is prefill and decode have distinct characteristics, right. In prefill we are analyzing a huge number of tokens, the sequence length is high. In decode we just need to all of our QKV matrix sizes are 1 by D, assuming we have KV cache, and then during decode we have to like access all the weight memory and all those things. So prefill and decode have different characteristics, right. So these two figures actually quantifies the different characteristics. So let's say during prefill we see throughput versus batch size characteristics. Now if we increase the batch size, throughput doesn't increase much, okay. So different color denotes the different input length, which you can see here. I mean, since prefill is compute bound, even if we increase the batch size, it will eventually oversubscribe the GPU, okay. I mean, it will schedule more compute than the GPU capacity, and then at the end the GPU will not be able to compute all the like prefill compute, all the compute related to prefill. So even if we increase the batch size, you can see the prefill throughput doesn't increase much, right. Now during decode the compute is less. I mean all the QKV matrices are of size 1 by D, and then no matter what is our batch size, we can do like Orca. If you remember, in Orca we can do this token level batching or the iteration level batching, so that we can merge the batches, and then for anything we need for any number of for any amount of batch size or for any batch size, we need to access the exact same amount of memory, right. So that's why you can see that if we increase the batch size, the throughput increases a lot during decode, right. So again, why? Because we can increase the batch size, the amount of if we increase the batch size, the amount of computation increases, but still the GPU can manage, because per batch the computation is already low. We already have seen that the arithmetic intensity of decode is already low, right. Now, so per batch, I mean, and again the amount of memory access is also like constant, right. We have to access all the weights. So for all these reason, we can increase the batch size to get higher throughput for decode while decoding, right. So prefill and decode have distinct characteristics. Now again, we can do continuous batching, but that causes interference. So for an example, let us say in this particular case, I am showing you one example where we batch R1 and R2 together in one GPU. Let us say we have just one GPU, we have two requests R1 and R2, the blue denotes the decode and green denotes the prefill. So let us say we have one GPU, so let us say we are performing this prefill and decode together, Now it might happen that we wasted some time for decode, right? If we launch this prefill and decode together, let us say we are not using Saarthi, then we are wasting the time for decode, even if we are using Saarthi, right? It increases the decode time a little bit, correct? So at the same time, there is some time wasted for prefill also, right? This much time is wasted for prefill. I mean, time wasted for prefill means we could have done some more prefill in that time if we wouldn't have another decode, right? Now, if that continues, like let us say instead of 1 GPU we have 4, so sorry, instead of 2 requests we have 4 requests, then you can see that the wasted time is like very high, right? These are all of these are the wasted time. So you can see if we do continuous batching, so here all these requests R1 and R2, sorry, R1 till R4 has been like batched together in one GPU. So if we do continuous batching, or if we make the batch size higher, then there is lot of wasted time. I mean, and again it will increase the entire batch time by a big margin, right? So you can see that the timeline here is much more larger than the timeline here, where we have only 2 requests in that batch, right? So the bottom line is we can batch, yes, but then the continuous batching will harm. I mean, it will waste a lot of GPU time. We can do co-location. I mean, when we say co-location, that means over provision resource to meet service level objective. Instead of 1 GPU, we can throw 4 GPUs. So in this case, let us say our time to first token and the service level objective is time to first token is 200 millisecond, and the service level objective for time per output token is, so time per output token and time between token are synonymous, is let us say 50 millisecond. If we have let us say 1 GPU and then let us say we are doing continuous batching, in this case you are seeing out of 10 requests, only 3 requests met the service level objective. That is a poor user level, poor user experience, and of course lower cost, only 1 GPU. Now we can throw 4 GPU to enforce parallelism, so that all the tokens or all the requests meet the service level objective, right? Of course we have a good user experience, but at what cost? We have higher cost, right? We are incurring higher cost. Instead of 1 GPU, we are actually spending now 4 GPU. The question is it worth? It might not be worth, right? I mean, if we spend 4 times cost, we want 4 times higher benefit. Can we guarantee 4 times higher benefit, or can we guarantee 4 times higher throughput? Straightforward answer is not always. In the next lecture, we will see how to actually guarantee higher performance with higher number of GPUs. Okay. So thank you very much. We will discuss the same thing in the next lecture. Thank you.